Hi, my name is Kacey Kim. I'm currently undergraduate student at the Colorado School of Mines, and I'm studying environmental engineering. And this year, I had the amazing opportunity to work with Jake Kurzweil, who's a PhD candidate, and also Dr. Terry Hogue under the first fellowship program at Mines. And I was able to assist in their research concerning hydraulic response to pre-fire mitigation treatments in Ashland, Oregon. And so just to start off, I will be talking about the background and how we knew that this research was needed by the public and the community. And I'll be kind of going over my methods and how I continue to work throughout this year and the results I've gotten from that and what future works can be done. And so just to start off, here's a diagram which shows wildfires and how they're increasing over time. And as you can clearly see that this is a very positive exponential trend, and this just illustrates that forest fires are increasing and that they're becoming a larger issue and will become a larger issue in the coming future. And so this next graph kind of shows how the snowpack and the water supply is impacted by the increase in forest fires as we're losing water supply and we're losing the amount of water that is available to the public. And so going off of this information, we're able to formulate our research question concerning how will forest fire mitigation treatments influence discharge in Ashland, Oregon, which is the treatment area. And so to start off this year, I began researching and analyzing other scientific journals from other researchers in order to kind of see how they were going about this problem and to become more familiar with the terms as well. And by doing so, I was able to become a lot more comfortable and understand much more where we're supposed to take our research as well. And so from that, I was able to become trained and well educated in R software, which is an analysis computer software program. And through that, I was able to learn how to create linear models and equations, and specifically this equation right here showing the rate of discharge. And by using many data sources, such as from DayMet, we were able to decide how discharge is influenced by precipitation and SWE. And so first I began formulating a calibration equation using the pre-treatment period data. And by using that, I was able to pull out the alpha and beta coefficients and use them for my other models, which was used for the west and east watershed areas in order to predict how treatment will affect discharge. And by doing so, I was able to create several graphs. So here's one of them. This shows the West watershed discharge graph. Just to go over what these mean, the blue is the raw data of the watershed, the red is the model that I was able to calculate, and the green is forest disturbances. And of course, this shows water year against the amount of discharge that was calculated or seen in millimeters for each year, and the percentages above them show the area attributed to each basin for the treatment. And this was also done for the east as well. However, as we can see here, for the east graph, we are less confident in this model due to the very similar R squared and mean squared values. And so for the results, once again, the R squared values were very high, and so that was very reliable as well. But as I said before, the West watershed showed promising results for the mean squared values, but as comparing them with the East, that wasn't very confident. So as in future references, I would love to continue working on that. But another thing that I was able to do through R was to separate the variables of SWE and precipitation and create another separate model outside of R in order to determine if there is an influence or relationship between these two. And I found that precipitation is the driving force in discharge rather than just SWE. And so another final result that we were able to find from these graphs was that climate seems, or the climate factor heavily influences the flow rather than forest disturbances. And this can be seen in 2014, 2018, which are drought years, and 2017, which was a water year, as you can see right here in this graph. And so with this, when climate is erratic, it determines the amount of discharge. And this heavily influenced our thoughts as this was kind of the opposite of what we were expecting, which was we expected discharge to increase with treatment, which is not the case here. And so for future steps, I would love, again, to further analyze the East Watershed with further data and also expand this model to different areas such as California, and also include recent data such as 2019 data as well. Thank you so much for listening. I hope you enjoyed and have a great day.